Hi friends. So today we shall discuss about single phase induction motor. Single phase induction motor, wide application is there in the practical field. It is used in fans, refrigerator, vacuum cleaners, washing machine, blowers, centrifugal pumps, small farming appliances, etc. We are adopting crores of motors in the practical field. Okay. So now we shall discuss about single phase induction motor, the basic concept. It consists of two parts. One is stator portion and another is rotor portion. Stator is connected to the single phase AC supply. And this is the rotor portion. This is the rotor portion, and the shaft. This is the shaft. This one. And then whenever you are giving the AC supply to the stator winding, a pulsating magnetic field will be created. A pulsating magnetic field will be created. Pulsating magnetic field means builds up in one direction and falls to 0 and then builds up in the opposite direction. Under these conditions, the rotor of an induction motor does not rotate because it builds up in one direction and then falls to 0 and then negative and then becomes 0. Due to this, the rotor due to pulsating magnetic field falls to 0 and then it becomes reverses and becomes 0. Under these conditions, the rotor of an induction motor does not rotate. Hence, single phase induction motor is not self-starting. But in case of three phase induction motor is a self-starting, whereas single phase induction motor is not self-starting. It requires some special starting devices. Once you give some special starting device when you introduce, then it will start rotating. That's why special starting devices is required to start the single phase induction motor. If the single phase stator winding is excited and the rotor of the motor is rotated by an auxiliary means and the stationary device is then removed, the motor continues to rotate in the direction in which it is started. So therefore, for starting purpose, we required starting winding is required, auxiliary means is required to start the motor. The overall summary is that single phase induction motor is not self-starting. It requires some special starting devices is required. Once it will excited by using special devices, then it will start rotating. Okay. So now we shall see the another important concept of double revolving field theory. Based on this, you can easily understand why the single phase induction motor is not self-starting. Double revolving field theory, this is the flux, okay, an alternating flux. Whenever you are giving the supply to the stator winding, an alternating flux will be created. That alternating flux, this is phi m, can be resolved. Any alternating uniaxial quantity can be represented by two oppositively rotating vectors of half magnitude rotating in opposite direction. An alternating uniaxial quantity can be represented by two oppositively rotating vectors of half magnitude rotating in opposite direction. Okay, this shown in figure A. And then this is the, if you add it totally, then you get a resultant vector pi m. And then now, this, rotating an angle, A is rotating an angle theta and this is minus theta B. And then if you add it vectorially, then you get phi m cos theta. This is rotating in this direction, this is rotating in this direction. And then whenever it comes to this position, shifted to this position A and this position, and now this become phi m by 2, this also phi m by 2. with opposing with each other, then it become 0. Okay, this is the thing. And then if you rotate, A vector to this side, A is rotating to this side and B is this one, and then when you add it vectorially, you get a minus phi m. And then further, shifted one angle, this one, and then this is the B one vector and this is the A vector, and oppositingly with each other, rotating in opposite direction, opposite direction. So now if you observe here, how the flux is, with respect to theta, how the flux is changing, theta flux is phi m, and then when you pass to 90 degree it becomes 0, and then 180 degree it becomes minus phi m, and then pass to 360 degree, once again it becomes 0. So with respect to rotation theta, the flux induced is changing. Okay, flux is changing. So alternating flux, this is the alternating flux. Okay, alternating flux can be considered as composed of two revolving fluxes, each of half the value and revolving synchronously in opposite direction, each of half the value and revolving synchronously in opposite direction. Okay, slip of the rotor is S with respect to the forward rotating flux. The slip of the rotor is S with respect to the forward rotating field. Slip with respect to the backward rotating flux is 2 minus S. Each of the two component fluxes revolving around the stator cuts the rotor, induces an EMF, and this produces its own torque. The two torque will be produced. One is called forward torque and another is backward torque, and are oppositely directed. Hence, the resultant torque equal to their difference. That I will show in the next figure. And the resultant torque is 0. Hence, the single phase induction motor is not self-started. So, therefore, one is forward field will be created and another will be backward field will be created. So, and oppositely with each other. So, due to that, what happened? Single phase induction motor is not self-started. Okay, so that you can analyze through this figure. If you analyze here, this is the torque versus speed characteristics of single phase induction motor. I already told you two torque will be created. One is with respect to S and another is with respect to 2 minus S. One is forward field will be created. Due to forward field, torque speed characteristic, you get a torque speed characteristic like this. Due to backward field, you get a speed torque speed characteristic like this. When you added here, this is plus is there, minus is there, cancel each other. Here it is 0. So therefore, this is the rotor speed is 0 at starting. At starting, why it is 0? Here, if you observe here, torque versus speed curve of a single phase induction motor, you can easily understand that. So due to one forward field, this is the torque producers. Torque due to forward field is TF, and torque due to backward field is TB is created. When you add it vectorially, these two torque, and then this is plus is there, this is minus is there, and then this become resultant torque will be, you get like this. Here if you observe the speed of a this is the speed and this is that synchronous speed. When it reaches slip is 0, torque is 0 here. So therefore, that's why single phase induction motor is not self-started, because two flux will be created. One flux will be in the forward field direction, it will produce, and another will be in the backward field. So due to that, what happened? Oppositely with each other. So due to that, single phase induction motor is not self-started. Okay. So now we have got different types of single phase induction motor. We shall discuss one by one. This is one type of this is the single phase induction motor. This is the rotor portion, this is the stator portion, this is the single phase supply, you have to give it here, this is the base plate here, this is main winding, and auxiliary winding. Some devices is required to start the motor. I already told you, because it is not a self started. That's why we are introducing another winding, that is auxiliary winding. This is the main winding. So this is the single phase induction motor. We are giving the supply here. So here it consists of two. This is the circuit diagram. This is main winding, and this is the starting winding connected with centrifugal switch. This is the rotor portion. So whenever you are giving the supply, single phase AC supply to the induction motor, a pulsating magnetic field will be created. That pulsating magnetic field can be resolved into two components. One is forward field and backward field. That is with respect to S and 2 minus S. And then, so due to that, it is not self-started. Through some auxiliary device, if you introduce, then it will become started. That we shall see in this with respect to the vector diagram. Okay. So now here, according to whenever you are giving, this is the supply voltage. Here, supply voltages. This is the supply voltages we are giving, and then this is the main winding current. This is the main winding current IM, and then IS. This is the starting winding. This is the auxiliary winding current or a starting winding current IS. This one IS and IM. If you add it vectorially, you get a total current I, and then angle is alpha. Angle between voltage and current is phi. This is the vector diagram of this resistor split phase motor. So it consists of, it is the one is main winding, I am represented here, and another is auxiliary winding. This is the auxiliary winding, including the centrifugal switch is added to the starting winding. Okay, and this is the vector diagram. I am taking voltage as reference because this value is more. That's why more lagging is the IM when compared to IS. This is the IS. Okay, and then vectorially if you add it IS and IM, you get the total current you are getting with an angle alpha. Okay, and voltage and current angle is phi. Okay, so now here whenever you excited the single phase induction motor with AC supply, whenever you are excited the induction motor with the AC supply, I already told you a pulsating magnetic field will be created. That when hits the rotor conductor, a rotating magnetic field will be created, and whenever it cuts the rotor conductor, an EMF will be induced in the air. Due to that EMF, current start flowing. That when a current is there under a magnetic field means torque will be created. Torque will be created. That will try to catch the stator, but it is always missing, and slip is existing, and then slip is always existing. And due to that, motor start rotation. The same as this one, three-phase induction motor. Whenever you are giving the single phase supply to the stator winding, a pulsating magnetic field rotating magnetic field will be created. That rotating magnetic field will be created by introducing auxiliary winding. And then whenever rotating field cuts the rotor conductor, here an EMF will be induced in the rotor conductor. Due to that EMF, current start flowing in the rotor conductor. Due to that current, current is there under a magnetic field means force will be created. Force will be there means torque will be created. That rotor will try to catch the stator, but stator is always missing. Due to that, slip is existing and torque will be produces, and then as usual torque will be produces. That we are utilizing for many practical applications. Okay, so now we are if you analyze the resistor split phase motor, we get a torque speed characteristic like this. Starting speed is 0, we get a starting torque, and then whenever motor, this is the synchronous speed. Whenever rotor speed reaches synchronous speed, torque becomes 0. This is torque, percentage of full load torque. Here this axis, this is the speed axis. I am consider here speed is 0. During starting speed is, rotor speed is 0. So due to that, speed is 0, but you get a starting torque. You get a curve, as usual curve we are getting. Whenever it reaches rotor speed to synchronous speed, slip becomes 0 and then torque becomes 0, and then you get a starting torque we are getting here. Okay, starting torque we are getting. So here applications where you are adopting means suitable for moderate starting torque required. Wherever you required moderate starting torque, you can adopt this register split phase motor. And then where we are using means fans we are using, and washing machines we are using, oil burners, small machine tools we are adopting. Power rating lies between 60 watts to 250 watts. We are adopting this type of resistor split phase single phase induction motor. So therefore it is clearly evident that here we are using we are using starting winding we are using and then this is the main winding and starting winding, followed by centrifugal switch. Whenever it reaches 75% of the synchronous speed, centrifugal switch is opened and it run with the main winding only, and then main winding only. So therefore, whenever you are giving the AC supply to the main winding, and then pulsating magnetic field will be created. Due to that rotating magnetic field will be created. Due to that rotating magnetic field, that will cut the rotor conductor. An EMF will be induced in the rotor conductor. Due to that, current start flowing in the conductor. The current start flowing is there under a magnetic field, means a force will be created in the conductor. So due to that force, torque will be created. That will rotating with the speed of n. This will rotating with the speed of ns, and then slip is existing always between stator and rotor. Stator and rotor, it will try to catch, but it's always missing, and then start rotating. That is the basic principle of single phase induction motor.